So please turn in those problems beginning of next class for a quiz grade. That gives you some idea of, like, when I'm sitting there just making up problems, like, that gives you an idea of, like, how you just saw how I create problems right there. I just write them down. Right? These seemed all doable. Every single group got every problem right. So I don't think there was anything way out. I think the logarithmic differentiation on 7 was really, really nice. If you would have tried it with quotient rule, it would have been a mess.
Well, yeah,
Same with 9, would have been a mess.
yeah, we did it both ways.
Yeah.
It was,
All right, it's time to move on. Make sure you do the homework for that section. The next section that we're supposed to cover, I'm going to start it today. I want to introduce you to it, all right? Because I'm just so damn excited about it.
don't we spend like 2 days on that?
We're supposed to spend 2 days on it. We probably will. But what I'm hoping I can do is free up a little bit of time for the curve sketching section, 4.4. I'd like to give us 2.5 days for that section. I just need more time later. If I can make more time later for us, it'll be good.
Hopefully this section won't put us in office.
Yes, this is Lhopitals Rule. It's actually Lhopitals. Okay, Lhopitals is named after a mathematician. Last name, Lhopitals. I don't know the first time, I forget it. This is one of my favorite rules in calculus. This is awesome. So let me just put up a couple of problems up here before we even start this section, because I need to remind you some stuff that we've already done that you may have forgotten. All right, so take a look at this example. Limit as, let's say, x approaches 2 of x squared minus 4 over x minus 2. So this section is about limits. Again, it's come back. All right, I know that doesn't make you happy, but once you see Lhopitals Rule, you'll be singing in the streets.
So 0 over 0.
Okay, you get 0 over 0. Everyone agree? What did we do to this in the past when we had 0 over 0? Some sort of algebra, some sort of something, right?
In this case, you could do
Yeah, what would you do here?
x minus 2x plus 2.
Yeah, difference of squares on top, you'd cancel a factor, and then you'd be in business. All right, so we can handle that. Thumbs up, we know how to do that. Next one, limit, let's say x goes to infinity of something like x squared plus x plus 1 over x squared plus 4. What do you get when you set this limit up? What form of a limit is this? Infinity over infinity. And do you remember how to do that one?
Yeah, some sort of algebra.
This one we divide quotient over.
Yeah, you divide, you look at the highest power on the bottom, you try and multiply by this 1 out here, which we would choose like 1 over x squared, 1 over x squared, pass it through. Okay, so we've had a way of dealing with that. Limit x approaches 0 of sine 4x over tangent 3x.
We split these up in tangent.
Yeah, you remember this? So this one always caused problems. You'd have to split it up as sine of 4x over 1, then split your tangent up and like try and
So we can jump over jump.
yeah, try and get that sine x over x, that junk thing, and make things appear and slide them over. This was a mess, but it could be done. It was just really messy.
And not like that.
Yeah. And then before all that, well, not before all that, but there was something in my notes where I told you this was an important formula everyone must know.
Yeah.
That was one. And we actually, to do this problem, we counted on that fact. And there was another one you were supposed to know. Which we didn't use as much, but it's this one, equals 0. So these were two limits that I asked you to just take on faith, but to know them. And then these were limits that we actually worked through. This one, not a whole lot of work. This one we had to imagine this hidden one in here and do some work. Here we had to rip it apart and do all this mess to it, right?
Cosine of x over x is just 1, right? If we approach 0,
Cosine of x over x.
then it's just 1 because it approaches 0.
No, that becomes infinite because you're saying without the 1 there. Without the 1 there? Cosine of 0 is 1. That goes to 0. You have fixed over 0. That's either infinity, negative infinity, or does not exist.
But we have like a range limit, right? So
Yeah, but we had to determine what they were. Like where they
All right, so Lhopitals Rule. Lhopitals Rule is going to allow us to do all of these limits in about, not that fast, but a lot faster than we were doing them, to the point that you're going to be probably pretty upset with me. Okay, so here's Lhopitals Rule. Here's what it says. Lhopitals Rule says, if you have a limit, and the limits, like what you have and what it's approaching, don't matter. You could have x is going to 0, x is going to infinity, t is going to 1. This doesn't matter, okay? So that's why I left little boxes there. Who cares what that is? And you have some function on top over some function on bottom. Call it f on top, g on bottom. If this limit is of the form 0 over 0 or infinity over infinity, and it doesn't even matter, this can be positive or negative infinity or positive and negative infinity, it does not matter. If you have infinite over infinite, regardless of the sign, or you have 0 over 0, if that happens, then if the limit exists, we have seen that sometimes the limit does not exist. DNE, right? Sometimes there's just no way to get a limit. But if this limit actually does exist, so here's what we have. The limit of this will be equal to the limit of this. Okay, so what is this saying? We're trying to figure out a limit, and we keep getting 0 over 0 or infinity over infinity. Well, if there is an answer, if this is an answer like 2 or whatever, maybe the answer is infinity, but if the limit exists, then whatever it is equal to the limit of what? It's the ratio of its derivatives. Amazing. But this is true. And I'm not going to prove this to you. This is tough. This is a tough one to prove. This is one of those proofs you just have to wait. If you ever want to prove that, you have to become a math major and then you can go prove it, okay? It's not simple to prove this. But it is so powerful because of what I'm about to show you. All right, so will you take that on faith? That's Lhopitals Rule. If you're struggling with the limit and you're getting these expressions, just take the derivative of the top, divide it by the derivative of the bottom, take that limit. Whatever that answer is the answer to this.
Does that work for second, third, and fourth points?
As long as you keep getting 0 over 0 or infinity over infinity, you can keep applying the rule. So let's do our first example.
And that is just on any number of derivative or just on the first derivative?
As long as you keep getting 0 over infinity, that keeps going. Oh, but the rule is, yeah, it's first derivative over first derivative.
Well, that's what I meant. I mean,
Yeah.
like, so if it's the nth derivative, as long as you're doing the nth derivative on both top and bottom.
I don't think, I'm not sure what you're asking. Are you saying, could I rewrite that as this and it would still be true?
Yeah.
No. It's the ratio of the first derivatives only.
Okay.
Okay?
That's what I was asking.
Yeah. But we can apply the rule more than one time, which I will show you an example of. All right, so let's go and apply Lhopitals rule to this example, which we could have done, you just said, we could have done by just factoring the numerator and denominator, right? You know what? Let's do it by doing that first. Let's do it the old school way first. So I would say, all right, I'm getting 0 over 0 here, right? So I would go limit, I would go x goes to 2, I would go difference of squares on the top, not difference of squares, just that on the bottom, right? Cancel these. So long as x is not 2, I can do that, but x is approaching 2, so I'm allowed to. And now I let x approach 2, and this right here gets closer and closer to what? 4. So my limit is 4, and I'm done. That's not so bad. But now let's use Lhopitals rule to do the same problem. So I start the problem off. I realize I get 0 over 0, right? Since I get 0 over 0, I'm allowed to use Lhopitals rule. So what I'm going to say is that this equals a new limit. And this new limit is still going to be x approaches 2. But instead of this ratio, I'm going to use the derivative of the top over the derivative of the bottom. What is the derivative of the top? 2x. What is the derivative of the bottom? 1. Now let x go to 2. And what do you get? 4. That's not a coincidence. That's Lhopitals rule. Okay, so I get 4, right? Now I have to, you have to, we have to show respect for L'Hopital and let people know that we actually used his rule. So what we usually do is we say that this limit is equal to this new limit. And I need to tell you I'm using L'Hopital's rule. So books do this different ways. Some books put an H here to let people know over the equal sign that they're using L'Hopital's rule. Sometimes they'll put an H and they'll circle it. I have always put an L and circled it for L'Hopital. You do whatever you want, I don't care. But you need to let me know that you use the rule. That all right? Isn't that awesome? Let's do another one. Why are you looking at me like that?
No, I'm saying it's intuitive.
Yeah,
It's intuitive.
it's very clean, isn't it? So what was the other one I had? I had put up here, what, x squared?
You also put x approaching 0, sine of 4x and x.
Oh, I'll do that one next. Let's do, the other one was limit x goes to infinity. X squared plus x plus 1. X squared plus 4? Okay.
How come you don't have to do quotient?
Pardon me?
How come you don't have to do any quotient?
Ah, I'm so glad you asked that. The question was, why didn't we have to do quotient rule? Okay, L'Hopital's rule has nothing to do with taking a derivative of a function, right? L'Hopital's rule has to do with how do you deal with a limit. And what he was able to show is that the ratio of this limit must always be equal to the ratio of the derivatives of the functions themselves. You are not applying a derivative to this. You are just differentiating top and bottom. So one of the big mistakes I see with L'Hopital's rule is that people will apply it and they're like, oh, that's quotient rule, and they do quotient rule. It's like, I'm proud of you for remembering quotient rule, but you're using it in the wrong place. L'Hopital's rule is always just derivative of top over derivative of bottom. That's the only time you can ever actually do that.
So that's why it's really important to stress not just do the differentiate both of them and say, oh, that's my new function.
That's right. Okay, so, oh, this was infinity over infinity, right? You must always check this first. If you don't have this, you can't use the rule. If you don't have 0 over 0, you can't use the rule. If you don't have infinity over infinity, you can't use the rule. But here I do have infinity over infinity, right? So I use the rule, L'Hopital, limit x goes to infinity, derivative of the top, 2x plus 1, over 2x. Agree? So now let x go to infinity. What happens? You get infinity again on top, right? And infinity on the bottom. So imagine now that this problem wasn't even here, and that's the problem I started with. That's still infinity over infinity, right? That's still valid for Lhopitals rule, so I will apply Lhopitals rule a second time. So it's like I'm starting over. And I'm saying this is equal to, by Lhopitals rule again, the limit as x goes to infinity of the derivative of the top over the derivative of the bottom. Derivative of the top, 2 over derivative of the bottom, 2. 2 over 2 is 1. That's the answer. As x goes to infinity, this goes to 1. Which is what we would have got had we come in here the old school way. We would have done 1 over x squared here, 1 over x squared here, distributed through, and then we would have done our magic and it would have gone to 1 also. Okay? Yes?
So why do we have to show that we're using this rule?
Because limits can't just turn, you can't just arbitrarily turn a limit into this unless it qualifies. And by putting this, you're not only telling me you've checked that it's qualified to use the rule, you're telling me what you did. Like, how does this limit transform into this limit? Are you doing algebra to get it from here to here? No, right? This was not algebra. From here to here, you didn't like come through with the hidden 1 or anything like that. You didn't rationalize a denominator. It's not algebra that took you from here to here. It's this rule. And that lets me know that as a reader. You know, if you didn't do this, then someone looking from how you got from here to here might be like, well, what did they do? Like, did they multiply on top and bottom by something? You get it? And it's so L'Hopital can be like, yeah, you know, got to give me some credit, right? Oh, no, he's long gone. No, he, you know, just that kind of like immortality type thing. He cares. The universe cares.
So when you call laws, you call them by their names.
All right, limit x goes to 0. It was sine 5x over tangent of 3x, right?
Sine 4x.
Oh, sine 4x. Tangent 3x? Okay. I hope you remember what this took for us to figure out. I hope you remember it, because it was confusing for a lot of you. Let's check first to see if we can use L'Hopital, and we're gonna hope we can. 4 times 0, 0, sine of 0 is 0. So I'm getting 0 on top. Tangent of 0.
Undefined.
Remember the graph of tangent.
0.
Tangent of 0, 0. So this is 0 over 0. L'Hopital. For those of you who watch my homework solution videos, I can already hear you making fun of me, because I sing L'Hopital when I do my problems. Every time I'm like, L'Hopital. I'm so happy to use L'Hopital. Like, I just, like, unintentionally, I'll just chant L'Hopital as I'm doing the problems.
That's not going to be a big problem.
L'Hopital should make you happy. All right, so derivative of the top. Cosine 4x times 4. Thank you. You still have to do chain rule. You are looking at the numerator by itself, okay? You do get to take just derivative of sine of 4x. That you know, you don't have to worry about the bottom, but you still have to apply any rules that are up there. So if it's sine 4x, you got to do chain rule. All right, how about the bottom? Secant squared of 3x times 3. All right. Let's let x go to 0 now. 4 times 0, 0. Cosine of 0, 1. Okay, so this is 1 times 4. It's starting to look good. Looks like I'm getting 4 on top. All right, secant of 3x, then I square it, then I multiply times 3. So remember, what is secant of 3x equivalent to? 1 over cosine of 3x. So if I plug in 0, this is a cosine of 0, right? And cosine of 0 is 1, so that's 1 over 1, that's just 1. But then you square it, who cares, still 1, times 3. Ah, that was nice. See how that worked?
Makes those easier.
Makes that a lot easier, yeah. Not every limit gets easier, though, with Lhopitals Rule. Most of them do. Most of the problems that you've done, if you go back and look at them now, you'll be like, are you kidding me? Like, you'll be upset about it.
So you did say that when we were doing the limits the first time,
I said what?
that we're gonna be mad at you.
One day?
Yeah, and you're gonna show us the rule.
Yeah, well, today's the day. What about that one? The one I said you have to know. Everyone knows that's 1, right? Everyone knows that's 1. But let's just use L'Hopital to verify. You get sine of 0 is 0, over 0, 0 over 0. Okay, L'Hopital. L'Hopital, so awesome. You get that? Right? That's derivative top and bottom separately. Cosine of 0, 1 over 1 is 1. Fantastic. All right, so we need to have a talk. Why did we have to do all that torture? Why not just do this? Get royalties, yeah. Why didn't I just show you this when we started limits?
Because we didn't understand what differentiation was.
Very good, that's the answer. I would have, but you wouldn't know what the hell I was talking about when I said, what's the derivative of sine x? The derivative is defined by the limit, isn't it?
Yeah.
The derivative started out with the limit. And then from that, we created differentiation, and then we came up with all these formulas. And so when you look at calculus, the heart of calculus, isn't that a cute heart? The heart of calculus is the limit. And from that, you have everything else. From this, you get the derivative. From the limit, you get integration, Cal 2. You get series, Cal 2. And just about everything you can think of branches from the limit. I thought there was a chart in here that showed it. One of the older books we had that we used had a really good chart that showed how the limit was like the basis for everything. Everything that we do is coming out of this idea of the limit. And it turns out that in order to do these limits, we can actually use the derivative in L'Hopital to come back and do limits. So that's why we don't introduce it to you in the beginning. Yeah. It just wouldn't have made sense. I would have had the carriage in front of the horses, and that, you can't do it that way. So we had to go through this loop in order to come back, and that's what we're doing now. We're doing an application of a derivative is Lhopitals Rule, which allows us to go back and do our limits that we were having trouble with a lot more ease.
How did he think of that?
I don't know. I don't know the history on how he was doing it. From what I can recall from L'Hopital, because I did at some point I knew something about him. From what I can remember, L'Hopital was kind of an introvert, and he was kind of a, just kind of to himself, and like this was his one big thing, his rule, right? So I don't know. Wonder if they have anything here. It's named after a French nobleman, Marquis de L'Hopital, 1661 to 1704, but was also discovered by Bernoulli in different, doesn't elaborate on that. So. You have to remember, you're looking, we talked a little bit about this. This is, thousands of years of thought here. This is not just like, we're trying to do in 16 weeks, which took hundreds and thousands of years for people to come up with. I mean, this is still a survey course. We're not getting into the fine details of this class, like any other class at a freshman, sophomore level would be. All right, last example. And then we're going to come back and we're going to spend a lot of time doing more of these because it's going to get not ugly, but we're going to start to expand the types of limits we can do. Right now we're pretty much stuck to like 0 over 0, infinity over infinity. But we're going to kind of blow that up a little bit. What's the limit as x goes to infinity of x to the 10,000th power over 2 to the x? Let's make that a little bigger. Let's go 100,000. Let's go 1,000,000 power. Let's go to the 1,000,000th power. And then do like a limit. No, I'll just leave it. How about that? What's happening? What are we getting on top? If x is going to infinity, you got infinity raised to the 1,000,000th power, which is like huge, huge infinity, right? Over 2 to the x, which is doing what? As x goes to infinity. Remember we studied this last class. Exponential functions look like this. 2 to the x would be growth because 2 is bigger than 1, right? The base is bigger than 1, so that should be growing also. Who wins? Does anybody win this? Which is getting bigger faster?
The bottom.
Bottom? If you go out, if you take this ratio and you start going out really far on it, do you think the numerator is going to dominate the denominator? Or do you think the denominator is going to dominate the numerator? Well, there's only one way to tell. Let's check it. We've got infinity over infinity. Why don't we use Lhopital? Yeah? Lhopitals Rule tells us that we can take derivative of the top and bottom. What is the derivative of the top? 1,000,000 x to the 999,999, right? Over? What's the derivative of 2 to the x? 2 to the x? Natural log 2. Good. All right. Did that help? This right here is a number. This right here is a number, right? Ignore those for a minute. What happens to the numerator as x goes to infinity right now? Infinity to the 999,999. That's going to get huge, right? Infinity over 2 to the x. Infinity again.
But if you keep taking the derivative, eventually that's going to be a 0.
So this is infinity over infinity. And if I do Lhopitals Rule again, this constant will be there, this constant will be there, won't it? But when I take derivative of x to 999,999, the 999,999 will come out, right? And then it'll be 999,998. Yes? But the bottom is going to be what?
So
2 to the x, and then another natural log 2 is going to pop out with that? Which is just another number. So I'm going to have 1,000,000 times 999,999 x to the 999,998, right? Over 2 to the x times natural log 2 times natural log 2.
Wouldn't you be right natural log 2 second time?
What do you mean?
Never mind, just a constant.
It's just a constant, so I just brought it with me. And then I get a new one when I take that derivative again. So here's a constant again, here's a constant, right? Ignore those. you get infinity over infinity again. But you can see what's going to happen over time. Eventually, the power of this is going to drop to a what? I mean, you're going to get this to go to a constant. Do you agree that at some point, if I keep doing this, the 2 to the x keeps on appearing, right? 2 to the x keeps on appearing, and then that eventually gets to like x to the first power. Agreed? So let's imagine we've gone all the way down to this point. We've done Lhopitals Rule like almost 1,000,000 times. We've got some constant on front. It's crazy looking, right? It's 1,000,000 times 999,999 times 999,998 times 999,000 times, you know what I'm saying? Yes? You know what I'm saying? I think that's called 1,000,000 factorial, if you've seen a factorial before. But who cares? It's some constant. And then we'll have x to the first power eventually, yes? And then over some huge constant. It's a bunch of natural log 2's, right? A bunch of them. And then
2 to the x.
2 to the x. On the next derivative, right? Because this is still infinity over infinity. On the next derivative I take, using L'Hopital again, limit x goes to infinity. The top is just going to be what? Some constant. Agreed? Constant. Big old constant up there. Over, and the bottom is going to be a constant, right? But then the 2 to the x is still there. Now the only thing that has x in it is this. And if I let x go to infinity now, you have a fixed number over infinity. And fixed over infinity goes to 0. So this limit is 0. Eventually, you go out far enough, the denominator will overwhelm the numerator. And that would have worked for any power of x. If you would have put 1,000,000 zeros after that, 2 to the x will eventually catch up to it. Eventually. That's why exponential functions are so much more, I don't want to say more powerful. They're just, when you talk about exponential growth, we're serious about that being like, that is serious growth. Because you can pick the highest power of x that you ever want and graph it, and the exponential function will eventually pass it up. It will happen. All right, sorry, I went over. Homework to focus on is the homework for the inverse trig function derivatives. And then make sure you do these problems, and those are going to be turned in for a nice, easy quiz grade, right? Have a great day. And I have, yeah.